Good afternoon, everyone. Everyone online, welcome to the sixth international seminar series of Javeriana University. Today we have a guest speaker. His name is Pejman Azarza. He's a Ph.D. candidate of the University of Victoria in Canada. So, good morning. He's got a bachelor in civil engineering in Mashhad University in Iran and a master's of science in the Sharod University of Technology, also from Iran. He's also got a master's of structural engineering in the Illinois Institute of Technology. So, Peshman, good morning to you in Canada. Good afternoon to everyone in the room. The webinar is yours.
Hi everyone, good afternoon. As it's mentioned, my name is Pejman Azarza and I'm third year PhD candidate. With nearly 3 tons used annually for each man, woman, and child. And I should also mention that twice as much concrete is used around the world than the other total other building materials: wood, steel, plastic, and aluminum. None of these other materials can replace concrete in terms of effectiveness, price, and performance for most purposes. So advantage of concrete, I should say the first one is resource efficient, and it has also manufactured locally, which minimizes transportation energy. It is also combined insulation with high thermal mass and low infiltration, and also long service life cycle industrial and absorb our waste. The earth. So based on the moderate UN scenarios suggest that if current population and consumption trends continue, the year of 2030, we will need the equivalent of 2 Earths. And of course, so we have only one. So here in the photo, we are at the crossroads now, and we have to make our decision and choose what is the right path to take. And most of the concrete mix design can be improved by reducing its carbon dioxide footprint. And exactly defines a successful building for sustainable development. I should put it in 5 key items. So first one is improving functionality, fits for its intended use. 2, ensuring longevity, an integral part of reducing cost and use of resources is durable, so it leads to long-lived structures. And the third one, enhancing environment importance and the resulting longevity of structures. So basically, when we increase the service life of any material, we somehow provide a solution for preserving the Earth's natural resources. But as I mentioned earlier, durability affects all 3 pillars of sustainability, which was environmental, economic, and social. So for environmental, durability can reduce the needs for additional materials, energy demands, and waste due to replacement. Buildings extremely durable material. Its durability is a function of mixture proportioning, mixing, placement, and curing. So any deficiencies in these areas increase concrete permeability and eventually create a corresponding decrease in concrete durability. So what is the definition of durability? A durable concrete is one that performs satisfactorily in a working environment during its anticipated exposure condition during service. Or in other words, when exposed to its intended service environment, such as marine site, a durable concrete will retain or remain its original form, quality, and serviceability. So as I quote the definition of durability. So durability of concrete to largely extent, it is commonly accepted that is related and it's been governed by its resistance to the penetration of aggressive ions such as chloride. And through the 5 mechanism, which I mentioned as a capillary suction, electromigration, absorption, diffusion, and permeation, these are all 5 transport mechanisms that is happening through the concrete structure. So about and this is maybe derived from an external source, such as leakage from the direct current power supply, but is also frequently caused by another factors such as electrical potential of pitting corrosion and reinforcing steel. Electromigration usually can be measured from the electrical resistance of concrete because it is only mechanism by which concrete can conduct electricity. We have the capillary suction, which is transport of liquids through a porous solid by way of surface tension acting in the capillary pores. So a variety of these physical or chemical mechanisms may govern this on the substance flowing or its local concentration or its environmental conditions or the pore of concrete structure, the porous structure of the concrete and the radius and the macro cracks presence. But the key in here, which most of the researcher and engineer propose, is permeability. Well known, this is the concept that is directly related to the durability. So one item is water. As probably all of us know, water is the most harmful agents to any kind of a structure, because with exception of mechanical damage, all the adverse influence on durability involve the transport of fluids through the concrete by the water. It can be through the solution, or it can be into the air, or other kind of items. And it also controls the rate of the deterioration. And also, when we have a permeable concrete, so the service life is going to decrease, and eventually we don't have any sustainable structures. So to clear your one subject, it doesn't mean the porosity of concrete. So we can have and also high permeable concrete. When we have the network of pores inside the concrete, which they are interconnected, which means we have high porosity and also we have a high permeability, which is going to reduce our durability. So as you can see in the photo, we have microcracks, we have voids inside the concrete, and all those voids is currently connected, which I can tell this is the high porous and high permeable. But in other words, if we have high porosity, but these pores are not internally connected, we may have lower permeability, which is kind of advantage as it's going to increase the durability of our material, which is concrete. Also, if we have low porosity and the pore size is small, it doesn't mean we don't have a permeable concrete, because all these pores can be connected to each other. So what factors affects transport and durability characteristics of concrete? So I summarize it in a table such that as you can see on the left type and degree of compaction. All these factors can somehow affect the properties of mix, which is mostly the porosity, matrix chemistry, and pore fluid chemistry. And all of them is related to all of the transport processes that I mentioned earlier. So one of them is diffusion, one of them is permeation, the other one electromigration, absorption, and so on and so forth. But all of this can create a pathway inside the concrete, and this pathway may ended up degrade our material. So, and also we have some deterioration process inside the concrete, which I mentioned as reinforced corrosion, which is the major one, and also sulfate attack, alkali silica aggregates, and also freeze and thaw. But I'm going to quickly go and explain these major processes, deterioration processes inside the concrete. So first, I'll start with the alkali aggregate reaction. When aggregates containing certain forms of silica will react with alkali hydroxide inside the concrete to form a gel, that this gel swells as it absorbs water from the surrounding cement paste or the environment. These gels later on can induce enough expansive pressure to our concrete surface, which leads to eventually the cracking inside the concrete, which is not a good item at all for the durability. Also, through another deterioration process, which is called freeze and thaw cycle, as we all probably know, freezing of water inside the pores is going to expand by 9% in volume, and volume of that water expansion may cause initial induced cracks inside the concrete, and it affects both hardened cement paste and also aggregate of concrete, and it's degrade our material. The other be present in concrete from for example. But these phenomena, when due presence of calcium hydroxide in the hydrated Portland cement paste, when the cement paste comes in contact with sulfate ions, both the alumina containing hydrates are converted to the high sulfate form, which, as you can see in the photo, is going to form heterangite, which is not good item for concrete, because eventually the growth of this crystal is going to induce the pressure to the concrete surface, and these are not also stable crystal, so they may disappear, which is a special case of internal sulfate attack. And if we do the X-ray analysis on the samples that already has been attacked by sulfate, you can see a peak of sulfur on the right-hand side in the X-ray spectrum. And I also provided the chemical formula for this process. But among all of these, based on the statistics, it has been indicated that over 40% of failure of a structure is due to corrosion of reinforcement. This is the chemical process to form the corrosion cell may be generated in two ways. So one way is the composition cell may be formed when two dissimilar metals are embedded in concrete, such as steel rebars or aluminum conduct pipes. Also, in the vicinity of the reinforcing steel concentration cells may be formed due to difference in the concentration of dissolved ions, such as alkalis or chlorides. So the corrosion is going to happen through the chloride attack or the carbonation. So when the level of carbon dioxide in the surface reaches to the rebar, it's going to reduce the pH level of the concrete, and eventually it's going to induce any stress onto the concrete surface, tensile strength, and eventually it's going to crack the concrete. Similar items, because when we have the different form of oxidation states in the iron, the photo on the right hand side shows the volume is also expanding by 6 times, which again is going to induce the pressure to the concrete wall, and we may have crack. Why I'm mentioning crack so many times? We have different type of cracks inside the concrete. So the cracks is going to come before serviceability, and it's also can be induced after. So the crack before, it's going to be at the earliest stage or fresh stage of the concrete, like shrinkage or settlement, and also from the construction during the some processes like chemical processes, physical processes, thermal or structural processes. But it is most comes from the process that I embraces is around $5 billion. In addition, because of loss in the production and traffic jam occur, indirect costs are also associated with concrete crack repairs. Besides all of these repair costs for our material, we should consider sometimes it is not really easy and it's not accessible for some of the structure that we can simply go and repair them. As you can see in the photo for the underground structure, this is the huge issue because the crack might not be available all the time. But always human learns from the nature. So for example, whenever you cut your fingers, you can see it start bleeding, but when the time passes, the crack or the cut in your finger is gonna see that is typically happens inside the concrete. So one is formation of calcium carbonate when the water is present. And it also the continuous concrete, which acts as a barrier, and also swelling from the cement matrix. So these all four mechanisms are responsible for the healing or sealing process inside the concrete. But there is an issue. You can't rely on this natural phenomena because sometimes it might not happen, or it's just limited to the certain crack widths, which is less than 0.2 millimeter, which is not a lot compared to other type of cracks that I mentioned. So recently, there has been great attention to the self-healing mechanism in the concrete. So it has been divided to two forms: autogenous healing, which I mentioned earlier, and also the concept of engineered healing or autonomous. So this concept has been dividing into three different ways. One of them is again improving the natural healing by using a polymer, or three different mechanisms. So the mechanism A on the left-hand side, the crack widths, which typically can be provided by using fiber inside the steel fibers, polypropylene fibers, and any type of fibers can provide us the limitation of crack widths, which gives the time to concrete to heal itself naturally. And also, as I mentioned earlier, the presence of water is important because carbon dioxide in the air is going to react with the calcium hydroxide inside the concrete and forms the calcium carbonate. Are going and see the historical on the concretes. And also, in a process B, as you can see, providing the water resources for the concrete to mold the concrete in the self-healing. One of the items that recently has been used is the use of super absorbent polymer, SAP. And this kind of polymer has a tendency to keep the water inside, and whenever cracks happens, they're going to release that water, and that water is being used by unhydrated, again is going to release and helps the concrete. But what I'm focusing now as part of my research study, as I mentioned, the strengths of the hydration products, or providing more crystals that acts as a barrier inside the concrete, which helps the concrete to improve. So I'm working on a technology called crystalline admixtures. So these crystallines, it's a hydrophilic materials which has a tendency to react with the water, hydrated cements, to make millions of microscopic needle-shaped crystals. As you can see in the animation, this crystal is going to form inside the crack, block the water pathway, and seal concrete from the out. And this admixture typically we added during the constructions. So as a part of my research, I mentioned earlier, I'm using these kind of admixtures, but still there are so many unknown questions. So one of them is, I couldn't find a research study that evaluates the self-healing capabilities of this admixture using durability, macromechanical, microstructure, and nanostructure tests simultaneously. And also, I couldn't find any well-standardized method that has been reported on how we can measure the efficiency of concrete when it's modified with this crystalline admixture. Also, long-term durability monitoring and life cycle assessment of this admixture is somehow lack, and it hasn't been addressed so far. Also, all the current construction design codes, guidelines, standards, I should mention that they consider concrete as a crack-free material, which is not true at all because concrete may not be prone to the cracking. And there's always cracking inside the concrete. So we should consider in our guideline the crack phenomena inside the concrete. So also, no research study I found that shows the interaction of crystalline admixture when it's combined with the Portland limestone cement. This type of new cement, it has 15% more limestone, and it has less carbon dioxide footprint, which makes this structure more sustainable because of using less clinker inside. So I divided my research study in 3 phases. So I went through the macroscopy and I wanted to see how these crystalline admixture perform in macrostructures. And also I wanted to quantify the reduction in the porosity and eventually in permeability, and also identify what would be the difference between different phases of hydration and chemical composition between the samples treated with this admixture or without. And also, I have some field samples, which I call the macro level investigations, to also see the effectiveness and durability of samples in corrosive environment using various NDT techniques. And also, I would like to develop a sustainable durability-based design model for my specimen. And at the end, I want to quantify the self-healing capability of this admixture to see the influence of this admixture when even it's interacting with the Portland limestone cement. And I also want to see various type of environmental exposure and its effect on the self-healing process. So I'll start with the phase 1 of my study. So for the phase 1, I mentioned it's the macroscopy. So first of all, I use scanning electron microscopy to see the structure and morphology of my samples. So I cast some mortar and also I break them and I just coated the fracture surface. You see how difference will be between the control samples, which doesn't have an admixture. As you can see in the photo, there's a crack inside. And also I cast samples that you can see the crystal growth inside the cracks, which is somehow give us an indication that this admixture perform best in the crack healing. Here also I put some of the photos that you can compare the control samples without admixture and the one with admixture. On the left hand side you can see the crystal growth inside, and those crystal eventually is gonna act as a membrane inside which blocks the water pathway inside the concrete and makes the concrete heal better. Even I went further because one waterproofing admixture or crystalline admixtures. So I extended to use 4 different type of these admixture which is commercially available. So as you can see, the key product is from the Crichton, which is the international company here in Vancouver, and also 2 different products from one company and the other one from the Penetron in here. As indication, all of them showed the growth of the crystals inside the crystals. So in order to identify the difference, so I've done the X-ray analysis on both product that is been producing by Kim or Crichton and also the other products. So as you can see, when I've done the X-ray analysis in X-ray spectrum, one of the critical component I need to look into it was if these crystals are earth-ringite. As I mentioned earlier, earth-ringite is not a good thing for concrete. So, and it can be indicated by presence of sulfur, and the sulfur, you can simply say in here that there's no indication of sulfur and there's no sulfur picking, which means there's no sign of earth-ringite. And also on the side, you can see the elemental mapping for different elements inside of the concrete. Penetron also is another product that I've used in my research. This also has showing the crystal growth inside. So as you can see in here, I tried to examine using the X-ray analysis. It turned out differently because this product, it seems, it's also inducing earth-ringite, which when you compare it with the other product, it's not a good thing for the concrete. So we need to be cautious whenever we are using this type of crystalline mixtures. So as you can see in here, there's a peak for sulfur, which indicates that earth-ringite inside. And similarly, I plotted the elemental mapping for these products. And also, to find the hydration products, I plotted the aluminum to calcium ratio and also silicon to calcium atomic ratio to identify different hydration phases inside the material. And as you can tell in here, so it's kind of spread around, but still they are aligning in the line of the calcium hydroxide and CSS gel, which is the main product of the hydration, and also CSH is responsible for the concrete strengths. Also, to identify if there is a gypsum, earth-ringite, or monocarbonate inside, I plotted the sulfur to calcium atomic ratio over the aluminum to calcium. And as mentioned earlier, one of the products out of 4, Penetron, it's somehow scattering around the earth-ringite and also monosulfate, which shows that these crystals or these products may not help in enhancing the self-healing and may be harmful for the concrete. Also, in our advanced microscopy facility, we are proud of having the highest magnification scanning transmission electron holography microscope, which is the one of the using this transmission electron microscopy, I was able to image the nanostructures of these admixtures. So I started with anhydrous or unhydrated particle. I put it under the SCM. The size of this particle was 40 to 150 micrometer. And then I sprayed the water on top of my samples on the powder, and I keep doing that for 7 days. So as you can realize, the formation of needle-shaped crystals on the right-hand side of the SEM image is obvious. And also all the particles is somehow swelling, and kind of hydration is going on inside those particles. But still, as I mentioned earlier, there is an issue when you want to see internal structures of your particles. The sample size that can be fitted inside the TEM should be less than 100 nanometer. And for satisfying that purposes, I use the focused ion beam, which is the macro milling machine, and I cut the samples, one particle, to have the electron transparent samples, as you can see in the photo. So this is the view of our stem, and you can simply say the particle has been cut into the degree that we can see electro-transparent, see inside. Then I start analyzing that nanoparticle using different technique. So I called it STEM analysis. So first of all, I divided these samples into the 5 regions. So the region, all of them, you can see it, it's indicated by a letter A, B, C, D, E. And I start imaging each of them. And as you can see from the scale, this is almost a nano-sized particle from the crystalline mixtures. And all of them, they show the compact homogeneous morphology. And also, to be on the safe side, I mapped the thickness of my samples. And as mentioned earlier, to have a good results, you need to have the sample with the thickness less than 100 to 50 nanometer. So as it turned out, my sample was in a good range. As you can see, all this blue is indication of 70 to 70 nanometer. And also, I went to see the morphology of my sample. So I used the electron diffraction pattern. And from this pattern, you can say if you have the crystalline structure, or you have amorphous structure, or you have something in between. So again, I divided my sample into the 5 regions. And from each region, you can see that there is no evidence of the crystallinity, but from the red arrow, or yellow arrow, I should say, you can see the short ordering range in this. But generally speaking, these samples turned out to be amorphous structure, because you can see it from the diffraction pattern in the middle of the photo. Also, I've done the X-ray analysis to see the chemical element inside. As it expected, it was silicon, it was calcium, and it was aluminum was the major elements inside. And as mentioned earlier, these are the conclusions that I've made. But this is the first part of my study. So the phase 2, which is durability monitoring of field specimen. So for this purpose, I had the mix design for the sample with the crystalline mixture and without. So I used 4 different type of mixtures with 2 different type of cements. And you can see my mix design on the left-hand side. And I started by doing it as a trial mix. So because I wanted to design a column that has a unique structure and that can hold the salt solution inside, because part of my study to see how this admixture performs in corrosive environments, and I wanted to simulate the marine sites within my samples. So I started with a small sample size. I used the PVC pipe, I used the sonotube, I used other type of material to see how can I get the hollow sections. Then when I casted a bigger samples, our goal was to have the column with 4 feet height. Then I realized that all of the rebars should be somehow concentric. So I went further and I designed a model in the SolidWorks. And as you can see, I managed to get a mold which can satisfy all these requirements. So using this mold, which has been manufactured in here, I was able to cast 25 samples. Out of these 25 columns with a 4 feet height, and also they have 12-inch outer diameter and 6-inch inner diameter. I get 18 of them which had different cover thickness of the rebar and different exposure. So some of them are exposed to the salt solution and some are not. And also some of them I was able to put the admixtures inside the mixture. And I've been curing them for 14 days, and then I expose them to the natural environment outside our civil material facility. And I start monitoring this sample since 2015, and since 2016 using several different non-destructive techniques. One of them is kind of my main focus, which is electrical resistivity. As I mentioned earlier, has a direct relationship to the concrete durability. And there are some non-destructive methods that you can use. So I use 2 different products. One of them is the Geotech, which is the Canadian-based company, and the other one is Recipot. So Recipot has a capability that you can simply go on the site and measure the resistance of the concrete. So on the photo on the right-hand side, you can see 4 probes in here, and these probes is gonna induce the current on the outside, and they're gonna measure the voltage inside. And using the Ohm law, you can have your resistance of the concrete. I also use the linear polarization resistance technique to find out about the corrosion rate of my samples. So I don't want to bombard you with too much information about my results, so I simply put a couple of graphs in here. So I divided my columns in the height into the 7 spots, and I start measuring them every 90-degree apart. So you can see for mono columns, the electrical resistance showed A, if you can see it on the left-hand side, the electrical resistivity is going to increase, and the main reason for that, because during the construction, the point A was our bottom sides, and probably it's got more consolidated because electrical resistivity of concrete is directly related to the pore structure and porosity, and also pore solution chemistry. So the compact the structure or more densified the structure, you expecting higher resistivity, which is also being proved. And also I mapped the concrete electrical resistivity through the whole columns, and you can see it on the contour map on the right-hand side. Then based off the classification that we have for concrete permeability, I tried to map these on a contour, and second contour on the bottom, it shows what, and from the others, I'm in a good side. Then I start comparing 2 different type of the columns, and as you can see, the one that has been treated with admixtures, in most of the spot it showed the higher resistivity, which is a good indication because it shows that you have less permeable structures, which kind of expected because those admixture is going to block those pores inside, and there is going to be resistance for the concrete to allow the electrical current pass. And this is also for 10 of the columns. So one or almost 3 items that I realized, it's the effect of edge. So the samples that you can see that has the higher value in the chart, those are the samples that I cast earlier, and they have older than the others. And also I realized that the one with the admixture has a higher electrical resistivity, and also some of these samples based on the cover thickness showed that the cover thickness also play an important role. So the one with which thicker cover thickness showed less showed higher resistivity. Then I would like to move on to the third phase of my study, which is self-healing characterizations. So here at UVic, we develop a technique, and this technique is patented. And basically, in this technique, as you can see, we have aligned 6 cylinders on the bottom, and these 6 cylinders is similar size that those cylinders is usually being used for the compressive strength test during the constructions on the site or even in the lab. And we are inducing cracks inside these specimens, and you can see we have water storage tank on top, and also there are 6 pipes goes inside that we are continuously monitoring the flow rate inside the concrete, and those flow rate is going to decrease during the healing process. This is what expected. So this is the kind of jig that we are putting it under the compression machine to induce the cracks inside our cylinders. And this is the setup for the test. So we have the water storage on top, and the water comes through the 6 pipes, and the head of the water is almost 1.5 or 1.6 meters. And we'll install 6 flow meter from Omega, and it is connected to the computer, and using the LabVIEW software, we are measuring the flow rate lively. And during that time, we can simply say how much our concrete cylinder is sealed or healed. So right now, it's a setup that I've been used for 2 different type of admixtures, 2 different type of concrete. So the one on the right-hand side is the one without admixture, and the one on the left-hand side is with the admixtures. So using the microscope, I was trying to see if the sealing process is happening inside, when also I wanted to measure the crack width and somehow related to the flow rate, because the higher the crack width, the higher would be the initial flow, which is kind of interest us. So in some of these spots, I can easily tell that, for example, on the photo on the left-hand side, that there are some white participants. Here it's probably silver, but it's been formed on top of our samples. And also we have similar items on the other samples. So the sealings, as a good sign, was happening inside the samples after I saw it under the microscope. And also from the flow rate, you can say the both natural healing and also the crystalline mixtures shown their effects on the healing process. So I had 3 cylinders for the control and 3 cylinders with the crystalline mixtures. For example, if you look into the blue line in here, you can see within a less than 300 to 400 hours, the flow rate dropped drastically, and it's reduced the flow rates inside. And this was from the samples that has been treated with the admixtures. And also we had quite large crack widths. It's 0.3. So you can see the average crack widths that I measured, and I mentioned in the graph on the right-hand side. And also, even for the lower crack widths with the initial flow was lower, the one with the admixtures, it shows that it's dropping more. But eventually, after passing almost 6,000 minutes, all of these samples is somehow healed, except one or two untreated samples, which the water is still flowing inside. Similar items, I tried to do it on the sample that I had the Portland limestone cement without admixture and with admixtures. So I realized that same phenomena is happening. So the one that is orange, gray, and dark blue in this graph, those are with the Portland limestone cement and the admixtures. And you can also say that they are dropping more than the others, which is a good indication of the self-sealing process is happening inside our samples. So to somehow conclude, I use the crystalline admixtures to improve the self-healing phenomena inside the concrete, to reduce the permeability, and eventually the reducing the cracking size and cracking amount, which is kind of critical for the repair process, because it's a costly process. And in some way, I enhance durability and improve the durability of concrete structures, which leads us to the longer service life and less repair cost. And what we believe in, we're going to make the concrete more sustainable. So this is the triangular that I really like. So sustainability, durability, and permeability, they are related to each other. And one day, hopefully, we'll see all the concrete structure is durable enough to have the sustainable world. As a future work, I quickly mentioned that for the macroscopy phase, I decide to have the SEM images, and I want to filter those images to just isolate it to see the pores inside. And then I would like to scatter all these images using the percolation theory to construct a 3D digital samples. And also for the field samples, for the columns, I'm trying to develop a model which I call it DuraCrack, because this model is going to helpful for the model for the concrete that has the cracks, and also it is including the self-healing process in the crack. When you have the self-healing inside, there's no need for consideration of larger crack widths, because you can count for that natural phenomena and also the one that we are engineering inside to have less amount and effort for the repair of those material. Thank you so much for your attention and for having me virtually through the web. If you have any question, I'm open to you. And hopefully I didn't.
Yes.
Hello? Can you hear me?
Yes, Pejman, thank you very much. Impressive work. I have a question
No worries.
of a professor. He just left the room because he had a meeting, but I'm going to
Okay.
ask on his behalf. The first question is on the penetron samples. What is the source of the sulfate you got on the samples?
So the source of sulfate is probably coming from their chemical compositions. So the chemical composition in the penetron samples is kind of coming from the admixture side. So we haven't induced any external sulfate inside those samples. So probably the company itself, when they are producing that admixture, maybe they intentionally put that sulfate amount to just have forming those needle-shaped crystals inside, and just somehow helping the concrete to temporarily seal or heal itself. But as I mentioned earlier, we shouldn't have that kind of crystal type, earth type inside, because they are not stable crystals and they're going to be removed simply easily from the mixtures.
All right, that's
Yeah,
very
this
good.
was
I have
something
a second question that
that,
says, did you attempt nano
sure.
indentation on your concrete samples?
Nano indentation.
Like when you do Brinell, or when you do one of these indentation in the surface, if you try to ident the surface of the nanocrystals you grew on the different cracks.
Oh, I didn't try that because I usually put the admixture inside my mixtures, and that was one idea we wanted to do it. We induce the crack and just put those crystal admixture inside and see the crystal growth inside. But still, when I saw into the fracture surface of those admixture, I was able to capture good images to see the crystal growth inside. But for the nanoparticle, for the manufacturing process, I just pick the samples very randomly from those hydrated particles that I showed early on this photo. So I just tried to, let me just go back to that photos. So here, the photo before, so when it's being hydrated, I just randomly pick the particles. Even I didn't try to just do it on the crystals. And then eventually I went through the cutting process and then took the photo kind of random from one side of the particle. So I'm not sure if I answered your questions.
I hope he got an answer on that. I'm trying to get into his idea, and probably Pejman, what he wanted to suggest you with the indentation test is that if you remember, when you do indentation on a surface, you have a clear
Okay.
understanding whether if the material is harder, the surface hardness could be stronger than before. So probably trying to attempt some kind of direct mechanical parameter, trying to compare the paste of cement compared to the
And he was
crystals that are growth inside of the crack.
talking in a nanoscale size or the in a micro level?
I think this is a micro level.
Okay, no, I haven't tried that one because I was only interested to see the morphology of our sample and also if it has the amorphous or crystalline structure. So I haven't done any mechanical, I should say, test or mechanical properties understanding about the strain or any stress inside the macrostructure. I haven't done that one, but this is a good idea if I consider later.
Okay, yes, this professor is very, very intelligent. Well, now, final question
Right.
I have, Pechman, is the following. What do you think would
Sure.
be the reaction of all those crystals if instead of pure water, you put this with wastewater that can have some type of mechanical, pardon, I'm sorry, chemical attack or chemical very harsh environment, and that when it gets in contact with the crack of the surface, what do you think would be the
Right.
expected behavior of these crystallites?
That's a really good question. I even thought about it a couple of times, and that's one of the idea that we put it in the salt solution, the columns. So we don't want to investigate the macrostructure for those columns, but at least we can see how they interact in corrosive environments. I still expect if those chemical is not harmful for the cement paste itself, they're gonna help the admixture because as long as the admixtures provided by the water is gonna, because it has the fine silica, it has the also cement component as a carrier of those polymer modified inside them. So those polymer modified inside these admixture, they are responsible for the crystal growth and the other component like cement and fine silica, they are responsible to forming a new type of the CSH or calcium hydroxide inside the concrete to just block that crack. This is the really good idea if someone look into it. I didn't get a chance to use the wastewater and see how they are performing. I haven't had any mortar type mixture to see what exactly is happening, but I'm guessing as long as the water is present and those chemical inside the wastewater is not harmful for the cement paste, they should do the job. That's my
Thank
expectation.
you, Pejman. I have a question of a student that asks if you have an idea, starting
Sure.
from which temperature the crystallite will create a self-healing process, or in other words, if this crystallite behavior is attached directly to the temperature of the environment.
So generally speaking, the concrete itself, in terms of the hydration products, and I'm expecting similar item for the crystalline mixture. So when they expose to the temperature, they react faster, and you will be able to cure these crystals faster. So imagine if the temperature is increasing, let's say by 5 to 10 degree, I would expect to have the growth of crystal faster and also seeing more hydration happening inside. But still, we should be careful because the level of temperature that we are increasing is somehow reduce the resistivity of our concrete. So when the resistivity of concrete is reducing, the aggressive ions like chloride, they get a more chance when the water presents to just come inside and penetrate inside our pore or cracks. But I think it's kind of balance between the growth of the hydration products and also the reduction in the resistivity.
Thanks, Pejman. There's the
But
last
definitely,
question, and it is if you expect a different behavior when you have a presence of salts in the environment because you're close to the sea.
right, yeah.
All right, Pejman. Well, thank you very much for your time. It was a pleasure
So
to
it
have
was a pleasure.
some slides and some insight of your research. Congratulations on it. It's amazing. I am completely sure you're going to get results that will be very important for the sustainability of concrete. And thank you very much for accepting this invitation of the International Seminar
Thank you for
Series of
having me over
Javiana. I hope
this.
you are willing to visit us if the time comes, so you can come and share this on person right here with us.
Sure, it's my pleasure whenever. So do you have any other question for me? You can also, you have my email, you can share with those students if they want to collaborate or they have some idea, or if they want to visit us in here, we are more than happy to show our facility, our university, or even our campus.
Well, we are going to get that invitation pretty seriously, so I'm going to send your email to everyone on the master's program, and if we have any person that
Sure.
is interested, I will let you know, so you can send us a proper invitation, like a letter from your university,
Sure.
maybe from your advisor, so we can arrange the whatever is needed to arrange.
Okay. Sure. Sure.
Thank you very much, Pejman, and have a good day, and thanks for your help.
You too. A wonderful day. Okay. Bye.